Supermassive black holes. Do they play with their food? Imagine a cosmic dance of destruction where stars get too close to supermassive black holes, only to be torn apart into cosmic spaghetti. But here's where it gets truly fascinating. A recent discovery suggests that these celestial monsters might not just consume stars whole, they might nibble at them over time. This revelation opens up a new chapter in our understanding of how supermassive black holes interact with their surroundings. A team of researchers has detected a star that survived an encounter with a supermassive black hole, SMBH, and then came back for seconds, almost 2 years later. This phenomenon, known as a tidal disruption event, TDE, is incredibly rare and has provided scientists with a unique opportunity to study these cosmic behemoths. The event, named AT2022-DBL, is the first confirmed case of a star losing mass to an SMBH and then interacting again, resulting in a second flare of light. Published in the Astrophysical Journal Letters, the study titled The Double Tidal Disruption Event AT2022-DBL implies that at least some standard optical tidal disruption events are partial disruptions, sheds light on these mysterious occurrences. Led by Dr. Lydia Macriani from Lancaster University in the UK, the research team analyzed data from multiple astronomical surveys to confirm the double flaring event. Supermassive black holes, located at the hearts of galaxies, exert a gravitational pull so strong that even light cannot escape. They play a crucial role in shaping the evolution of galaxies. Our own Milky Way harbors one of these giants, discovered through the peculiar orbits of nearby stars. During a TDE, a star passing too close to an SMBH is stretched and torn apart in a process often described as spaghettification. Stellar material forms a stream that can loop around the black hole, with some of it falling into the accretion disk, causing bright flares visible across the electromagnetic spectrum. However, not all TDEs behave as expected. TDEs are categorized into X-ray and optical types based on their emissions. X-ray TDEs, the first type discovered, emit powerful X-rays and follow a predictable pattern. Optical TDEs, detected by automated surveys, emit little to no X-rays, but are strong in optical and UV light. This discrepancy puzzled scientists, leading them to question why sub-TDEs are less luminous than expected. AT2022-DBL offers a potential explanation. SMBHs might be consuming stars in smaller portions rather than devouring them entirely. This partial disruption theory could account for the variability and brightness observed in optical TDEs. The researchers analyzed the light curves and spectra of AT2022-DBL's two flares, finding them remarkably similar, except for differences in intensity and decline rates. They ruled out alternative explanations, such as gravitational lensing or separate events involving different stars, concluding that the same star was involved in both flares. Professor Arkavi from Tel Aviv University expressed optimism about the possibility of a third flare in 2026, which would further support the partial disruption theory. He noted that even if no third flare appears, the findings challenge our current understanding of TDEs. Another intriguing possibility is that the difference between X-ray and optical TDEs could be due to observational angles. In edge-on systems, X-rays might be absorbed by debris disks, re-emerging at lower energy levels as optical or UV light. This angle-dependent effect could explain why some TDEs appear to lack X-ray emissions. If the partial disruption theory holds true, it would require a re-evaluation of TDE emission mechanisms and the factors influencing their visibility. This discovery underscores the complexity and mystery of supermassive black holes and their interactions with the cosmos. What do you think? Could supermassive black holes indeed be playing a game of cosmic tag with stars? Share your thoughts in the comments. Star survives black hole encounter twice. Scientists shocked by new discovery. Imagine witnessing a star's narrow escape from the clutches of a supermassive black hole, a cosmic drama that unfolded in the vast expanse of space. In February 2022, a sudden blue-white flash caught the attention of astronomers worldwide, marking a dramatic event involving a star cataloged as AT 2022 DBL. 2 years later, another flare erupted from the same spot, as if the universe was replaying a scene straight out of a sci-fi movie. Dr. Lydia Macriani of Lancaster University and her colleagues at Tel Aviv University embarked on a mission to unravel the mystery behind this cosmic double act. Their research led to a fascinating discovery that challenges our current understanding of the universe. A tidal disruption event, TDE, occurs when a star ventures too close to a supermassive black hole. The black hole's immense gravity stretches the star, causing half of its gas to fall inward. This triggers a brief beacon of light that can last for months. Since black holes themselves emit no light, flares like these offer a rare glimpse into their size, spin, and appetite. But AT 2022 DBL broke the usual script. The second flare arrived 711 days after the first, mirroring its temperature and spectrum, yet shining 4 times fainter. Both flares were cooler and dimmer than what classic accretion disk theory predicts, echoing a decade-long puzzle in optical TDEs. The light spectra show helium and nitrogen lines, typical of the so-called Bowen subclass, with an unusually weak hydrogen signal. This suggests that only part of the star's outer layer was stripped away during each pass. The decline rates were different too. The first event faded quickly, faster than a typical full disruption, while the second faded more slowly, matching what's known as partial stripping. This event suggests that stars might lose mass in stages rather than vanishing all at once. If partial disruptions are common, then many stars may survive their first encounter and return, potentially more than once. This raises thought-provoking questions about how different stars respond to tidal forces. Larger or puffier stars might shed more gas, while denser ones could hold together longer. This variability could reshape our understanding of star-black hole interactions. But here's where it gets controversial. Could 2 unrelated stars be shredding in the same galaxy so soon? The odds are incredibly low, less than a 1 in 1,000 chance for a quiet galaxy like this. Gravitational lensing also fails to explain the phenomenon. Simulations show that a star on a 700-day, highly elliptical orbit around a black hole at that distance could lose outer layers on each pass, yet keep its core intact. Such orbits can naturally form when a binary star system passes close to a black hole, a process known as the Hill's mechanism. This discovery challenges the assumption that most tidal disruption flares are isolated one-offs. With AT 2022 DBL showing repeat behavior, observatories may need to adjust search strategies to track follow-ups over multiple years. This also affects how flare candidates are prioritized for follow-up, as events that fade quietly might still have another act ahead. The implications of this discovery extend far beyond a single star. Repeated nibbling could help explain the missing energy problem in optical ultraviolet flares, which consistently radiate only a fraction of the energy expected from swallowing a sun-like star. If many of the events in current catalogs are actually partial disruptions, the true TDE rate may be higher than we think. Models of disk formation would also need to factor in super-Eddington flows, which can hide energy in winds or jets. Astronomers will keep AT 22 DBL under close surveillance, eager to see whether the star still has the strength for an encore. This cosmic drama is far from over, and its outcome could rewrite the rules of stellar survival in the universe. Thought-provoking question? Do you think this discovery will change how we view the relationship between stars and black holes? Share your thoughts in the comments below. Stars' incredible escape from supermassive black hole, a cosmic phenomenon. A star's daring escape from a black hole and its bold return. In an astonishing turn of events, a star has managed to break free from the clutches of a supermassive black hole, only to make a surprising comeback for a second encounter. This extraordinary occurrence, observed by astronomers, defies conventional beliefs about the interactions between black holes and stars. The cosmic ballet begins. The astronomical drama unfolded when a distant supermassive black hole attempted to consume a star from a galaxy millions of light years away. Rather than being overwhelmed by the black hole's gravitational forces, the star managed to escape, capturing the attention of researchers. The first indication was a flare, a sudden burst of light indicating the star's initial close call with destruction. To the astonishment of astronomers, about 700 days later, a second flare appeared, almost identical to the first. The event was officially named AT-2022-DBL, and the team responsible for the discovery quickly dismissed the notion that two different stars were involved. Instead, they concluded that the flares were caused by the same star experiencing two separate bites from the black hole. Understanding tidal disruption events, TDDs. To grasp the significance of this discovery, it's crucial to understand tidal disruption events, TDEs, a phenomenon that occurs when a star ventures too close to a supermassive black hole. Black holes, which are found at the centers of most large galaxies, have such powerful gravitational pulls that anything crossing a certain threshold is pulled apart. As a star gets too close, the black hole's gravity stretches and tears it apart in a process called spaghettification. Some of the star's material falls into the black hole, while the rest is ejected into space, often producing spectacular flares of light. For years, scientists have observed TDEs, but these events had typically been seen as one-time occurrences, with stars destroyed in a single dramatic event. The flares that follow such disruptions can last weeks to months, illuminating the region around the black hole. But recently, some TDEs have exhibited behavior that didn't quite match expectations. The star's return. What lies ahead? AT-2022-DBL raises the possibility that not all TDEs result in the complete destruction of the star. Instead, it suggests that some black holes may prefer a slower, more drawn-out meal rather than immediately consuming their prey. If this star survived its second encounter, it could return for a third round of flares, continuing the cosmic spectacle. Researchers now eagerly await the next flare, which they expect in early 2026. If a third flare appears, it would confirm the idea that the star wasn't fully destroyed during its second encounter, leading to a re-evaluation of the nature of tidal disruption events. However, if no flare appears, it would indicate that the star met its end during the second round, though the similarities between the first two flares would suggest that partial and full disruptions might look the same. This would provide strong evidence that not all TDE flares are caused by total stellar destruction, a discovery that could change how scientists interpret these events. As researcher Ayer Arkavi from Tel Aviv University notes, if we see a third flare, it means that the second one was also the partial disruption of the star. The research team is now working to determine whether AT-2022-DBL is part of a much longer cosmic performance.